probably eventually discover that they're quite representative of the questions in the exams. So you are strongly encouraged to work these questions yourself. And if you have any questions about those exercises, I will be happy to respond to them. But I don't do them without any prompting.
For sure. Thank you, Professor.
Okay. Any other questions?
I have a question, Professor. So the exam is take place at the same time with the class?
Absolutely.
Okay, thank you.
It is basically a face-to-face class, except it happens remotely. So from that point of view, you're expected to attend class. I do not record it, and the exams will be exactly at the time that the class meets.
Are the practice questions already out, or you haven't put them already? Oh, okay.
Exercise sets 1, 2, and 3. They don't do you much good right now because you don't really know anything about what would allow you to answer those questions, but certainly you can look at them.
Professor, so the exams are going to be the written exams. Are we supposed to upload it to PDF or something, or how is it going to be like?
We have a system where you basically have to create a single file, and that single file has to be sent to that system. I will announce the format in which you have to do that later. It's not very complicated. All you have to do is create a single file that contains all your answers to the questions, and then it will be uploaded essentially like an email.
All right, thank you.
Okay. Any other questions? Sure. Exercise set 1, exam 1. Exercise set 2, exam 2. Exercise set 3, exam 3. No, you will not get the answers. The question is not one whether you get the answers or not. For the most part, the exercises are things that you have to do yourself. I can show you many times how I ride a bicycle, but unless you actually ride the bicycle yourself, you will never learn how to ride the bicycle. So I am perfectly happy to answer specific questions about specific questions in the exercise set, but I do not just wholesale give you an answer because number one, not all questions have a unique answer, and number two, the issue here is not the answer, the issue is the process how to get there. Any other questions? All right, so we started informally, and today we will make this a little bit more formal. We started talking about words and about language. So as we said, there's an alphabet. This is a finite, non-empty set of atomic symbols, and a word is a finite sequence of letters. Obviously, there can be repetitions, so don't overthink things. This is just like what you would think a word to be. In a binary string is a binary word. A decimal number is a string. is a word over the alphabet 0 through 9. An English word is a word over the alphabet A through Z, and so on and so forth. So this is, there's nothing particularly challenging about it. What is important is that words are finite, so they have a length. And the length is the number of letters in the word. So if you have a word W, and as I said, a star is the set of all words, and I'm being overly specific of all finite words over the alphabet A. So if W is an element of A star, then the length of W is denoted by absolute values for W. So this is the length. And so if we have A is little b, then A, B, A would have a length 5. So in particular, there can be repetitions, and obviously you have to count every letter as many times as it occurs in order to get the length of the word. There is a special word which is the empty word. And we will denote it by epsilon. It has the length 0. In other words, that finite sequence of letters that we use to define a word, that finite sequence has 0 elements. So obviously this is a unique word because there is only a single empty word that conforms to the definition of having 0 letters. Now there are a number of properties that we're interested in, and in particular, when it comes to words, we have an operation which is concatenation. What is concatenation? Well, it is basically taking the finite sequence of letters of the first word and taking the finite sequence of letters of the second word and creating a new sequence that contains the letters of the first word followed by the letters of the second word. I am basically belaboring what is fairly obvious, and so it is important that you don't really overthink this. If you have 2 words, then you can, of course, create a new word by concatenating those 2 words, and that will give you another word. The empty word, of course, has the property that for all words V in A star, the length, the V concatenated with epsilon is going to be equal to epsilon concatenated with V, which is equal to V. So the empty word, in a way, acts like the number 1 in numbers under multiplication. So if I have a number and multiply it with 1, then obviously this is the same thing as taking 1 and multiplying it by that number, and that will simply give you that number. And so concatenation is an operation, and the empty word then acts like the unit under multiplication for numbers. So this is really not particularly deep or anything. The concatenation is a fairly straightforward multiplication, fairly straightforward operation that is similar to multiplication of numbers. Now, in contrast to the standard multiplication for numbers, concatenation on words has other properties, or more specifically, lacks a certain property, and that is commutativity. So when we look at concatenation, then it has a number of properties. So, for instance, it is associative, which means that if I have a word U and V and W, all arbitrary words, then U concatenated with V and the result concatenated with W is going to be exactly the same as taking V and W and concatenating U with that. So that is a fairly straightforward idea that follows immediately from the way words are defined as sequences of letters. So the concatenation, of course, then will create a sequence of letters, and it doesn't make any difference in what way you're going to form those new sequences. They ultimately will all be the same. So associativity holds, commutativity does not. This is not commutative.
Professor, are you recording the lecture for us?
No.
It says that it's recording at the bottom, so that isn't you.
I am recording it occasionally for my own purposes, but officially there is no recording.
Okay, thank you
Okay?
for clearing that up.
At least not a recording by me, as I said. If you are enrolled in this course, you're certainly entitled to record for yourself. That's fine. So the operation concatenation is not commutative. That's, of course, fairly obvious if you think about it. Even in ordinary language, if you have the word house and you have the word dog, well, there you can have, if you concatenate them, you have house dog, or if you do it the other way around, you have dog house. Well, nobody would ever expect that a house dog is equal to a dog house. So it is obviously not commutative. Now, that, of course, is the issue that can be, commutativity can be achieved under certain circumstances. For example, if your alphabet consists of a single letter, then obviously the property that is relevant of a word in A star, if A is a single letter alphabet. The property that defines what a word is simply the number of occurrences of that letter. And since the length then is the only relevant aspect of a word, because the only letter is the letter A, that means that if you have two words that are concatenated, obviously the length of, in general, if you have U concatenated with V, that is simply the sum of the lengths of the constituting words of the concatenation. So if the alphabet consists of a single letter, then obviously the number of occurrences of that letter is what is relevant. And that means that obviously if we have two words over that alphabet, then U concatenated with V is equal to V concatenated with U for all words over that particular alphabet, because U and V, the essential quality is the length, the number of occurrences of the letter A. And so whether you take first however many there are in U followed by however many are in V, or whether you first take however many there are in V followed by however many there are in U, doesn't make any difference. The result is going to be the same number of letters, occurrences of the letter A, and so commutativity in that particular case holds. However, in general, that is not the case, as I've already indicated. Yes?
So why would this in particular be an important point? So like, is this because we're looking for duplication and maybe we can actually, turn down operation costs, or is there some kind of, overarching theme that the reason why we're looking for commutativeness?
Basically, we're looking at the question, what kind of properties do these creatures have? So we have established that they're associative, which means we don't have to parenthesize anything. We basically can forget about the parentheses, because if it doesn't make any difference in what order you do that, you will probably say just UV instead of UV, then the result concatenated with W, or something, some other parenthesization. But it is not commutative, and that is a property that is important, because in many cases commutativity is something that you expect. Addition and multiplication in the number systems are whatever number system, integers, real numbers, imaginary numbers, whatever, they're all commutative. Concatenation in general is not commutative. Okay?
Thank you.
So we have defined the length, we have defined concatenation, and now we can define a language. Well, a language is in fact a misleadingly simple thing. It is a subset of A star. Any subset of A star is a language. So that looks very simple, and it turns out to be not quite as simple as it appears to be. Now, the first thing that we will have to look at is what kind of operations there are. Now, by virtue of the fact that any language is a subset of a universal set, and of course we will assume that the alphabet A is fixed. So if we say a language, we usually don't add over the alphabet A. That tends to be implicitly understood. And so if we have a language, then that is assumed to be a subset of A star, and the A star is a constant, if you will, because the A is going to be fixed and a constant. So all languages in a particular discussion will be assumed to be over the same alphabet. And so that implies, of course, that because they are subsets of a universal set, we have all set operations. So this is basically imported from set theory. We have union, intersection, complement. All of these are operations that we can apply to a language. So this is a language because we get those from set theory, because any language is a subset of A star. We can apply all the set operations. So if we have two languages, L1 and L2, then we can, for instance, do the union of those two. We can do the intersection of those two, or we can do the complement, which would be A star minus L1. Anything in A star that is not in L1 would be the complement of L1. So these are...
Professor?
Yes?
So A star is the set which contains all possible combinations of letters within the alphabet, correct?
Correct.
So the language is also a set of combinations of letters, say words, but not the entirety of all of the possible combinations?
Absolutely.
Is that fair? Okay, thank you.
But, I mean, wait. It doesn't have to be. Of course, A star in it by itself is obviously a language.
Could you possibly give like a brief definition of what you mean when you say language?
There it is.
Okay.
I think what maybe if we think about language being a superset of A, includes everything plus.
It isn't necessarily a superset of A, because that would assume that every letter in the underlying alphabet would in fact be a word in the language. For example, I could define the language of all words of even length. Okay.
I'm sorry, could you tell us what exactly A is? What is the set A? What does A contain?
It is an alphabet, a finite non-empty set of atomic symbols. And as I said, think of it as the English alphabet, think of it as the binary alphabet, 0, 1, think of it as 0 through 9. All of these are alphabets because they conform to the definition that this is a finite, non-empty set of atomic symbols.
Okay, so A star would be just all possible combinations of the letters
All
in
possible
A.
sequences of letters, correct.
Okay, thank you.
So somebody asked Unicode. Yes, Unicode would be a finite alphabet, and therefore it would be perfectly acceptable as A, and then you of course can construct A star from that. You can construct A star from any alphabet as long as it has at least one letter. That's why we're stipulating that it be non-empty. If it were empty, then of course there wouldn't be any particularly interesting stuff arising. But when you have one letter, then it is clear that A star is infinite because you have 0 letters, 1 letter, 2 letters, I'm sorry, 0 instances of that one letter, 1 instance of that one letter, 2 instances of the one letter, 3, 4, 5. Obviously, there's no limit. So obviously, there are words of arbitrary length, and it follows, therefore, that A star, even if A contains only a single letter, is still infinite. So A star is obviously always infinite.
Professor?
Yes?
So with the difference, since A star could in itself be defined as a language, what's the difference between A star and L? Would that be definitions put in place?
A star can be a language because obviously A star is a subset of A star.
Mm-hmm.
And given that definition of a language, any L that is a subset of A star is a language. It follows, therefore, that A star is also a language.
Okay.
So could it be said that a language is the rules that the alphabet follows?
At this point, we're not looking at any particular rules. We're not looking at any of the mechanisms to define languages. At this point, we simply have a generic mathematical definition that doesn't necessarily allow you to make any particular conclusion about that language other than that it is a language. Any subset of A star is a language. So we have obviously A star, a language. That is the most comprehensive language. There is nothing that is not in that language. The least comprehensive language would be the empty set. The empty set is obviously a subset of A star, and therefore, by definition, it is a language. And in between of these, you have an awful lot of other languages. Okay? So, what kind of operations do we have? Well, we've already said we have set operations. Set operations, union, intersection, complement, that is simply inherited from the fact that these are subsets of a universal language, A star. In addition to that, and that has really nothing to do with the way A star is formed, it does not use any of the notions that all the elements in A star are words. That comes now. We have concatenation. Now, we've already defined concatenation of words, which is relatively simple. Each word corresponds to a sequence of letters, 0 or more of them. And so when we concatenate two words, then we take the corresponding sequences, make a new sequence that contains the sequence of the first word followed by the sequence of the second word, and that'll give us another sequence, which of course means it is a word. But we can then extend that to languages. So we have two languages, L1 and L2, subsets of A star. We can define L1 and L2. And that is simply the set of all concatenations, V1 concatenated with V2, such that V1 is in L1 and V2 is in L2. Now there is a fairly straightforward and obvious connection between concatenation and the Cartesian product. L1 and L2 are, of course, sets, and as such we can form the Cartesian product of those two sets, and that would then simply be the set of all pairs V1, V2, such that V1 is in L1 and V2 is in L2. And it looks as if this is really the same type of definition, but it turns out not to be quite true. And so let's look at an example. Say we have L1 equal to L2 equal to epsilon A and AA. So these are two finite languages, and we are simply going to look at the concatenation of those two languages. So this is L1 concatenated with L2. Well, what does that mean? You take a word from the first language and you take a word from the second language and you concatenate them together. So you can do epsilon with epsilon, for instance. Okay? Or you can do, so let's just fix V1 to be epsilon, and V2 ranges over the 3. So we have epsilon with epsilon, epsilon with A. What does it do? All right, epsilon with A, so we take V1 in L1 to be epsilon, and then we let V2 range over the 3 possibilities, epsilon, A, and AA. So that is having V1 being epsilon. Then we have V1 being A, and we let it range the second word again over the 3 possibilities, A concatenated with A and A concatenated with AA. And finally, we're going to make V1 two A's, followed by the V2, which is epsilon or A or AA. And now if you look at that, that of course is exactly what you would get from the Cartesian product, with one big difference, that this epsilon concatenated with A is of course exactly the same thing as A concatenated with epsilon. Therefore really we have it already and we don't need it anymore. And then epsilon with AA is the same thing as A with A, so we have that already. Now, 3 A's we don't have yet. 2 A's we have already. There they are. 3 A's we have here already. And finally 4 A's. So effectively in this case, we can sort of simplify this. This is epsilon, or 1A, or 2 A's, or 3 A's, or 4 A's, and that is all there is to it.
Sir,
Why you cancel two A's? We don't have anymore.
Because I have epsilon with AA.
The other one only 2A. So
It doesn't make any difference.
okay.
That's the whole point of concatenation. Epsilon concatenated with anything is that anything. So it's epsilon A, AA. And then we have 3 A's and we have 4 A's. This is A concatenated with epsilon. We got this already. This is A concatenated with A. We got this already. This is 3 A's. We haven't got that yet. 2 A's with epsilon. We've got that already. 2 A's with another A. That's 3A. We got that already. And finally 4 A's. Okay? So that means basically that in contrast to the Cartesian product, which would necessarily have 9 elements because we have epsilon with epsilon, we have epsilon with A, we have epsilon with AA, and then we have A with epsilon, and we have A with A, and we have A with AA, and finally we have 2 A's with epsilon and 2 A's with A and 2 A's with 2 A's. These 9 pairs are all different. So if we have epsilon, the pair consisting of epsilon and A, that obviously is different from the pair consisting of A and epsilon. However, if we do the concatenation, the concatenation of epsilon with A is of course exactly the same as the concatenation of A with epsilon. Therefore, we record this only once. So there, the Cartesian product has 9 elements in this particular case. The concatenation, on the other hand, has only 1, 2, 3, 4, 5. So it is concatenation is very similar to the Cartesian product, but it is not the same, because in concatenation, we identify certain sequences with each other. So the sequence of epsilon followed by A is exactly the same thing as the sequence of A followed by epsilon. And so we write it only once down. So this set, the concatenation of the language epsilon A and AA with itself has 5 elements, but the Cartesian product has 9.
Sorry about this, Professor, but which one of these equations is the Cartesian one? Is it the second one?
This is the Cartesian product.
Okay.
And this is the concatenation. So obviously, if you have finite languages, as we do in this case, the elements in the Cartesian product is going to be an upper bound on the number of elements in the concatenation. It can be exactly the same, but it can be less, as this example shows. Epsilon is not the empty set. Epsilon is an empty word. Okay, this is important. Epsilon is the empty word. It's unique. It is a word. It consists of 0 letters from the alphabet. Any other questions about this? Then we have All right. Sorry. What was the question? I didn't get it. All right. So I indicated that epsilon is a word, a unique word, a single unique word that contains 0 letters from the alphabet. It is not an empty language. This is a different story. We'll get to that later. So L is a language, and we can define now powers of L. L to the I is, well, the language consisting of the empty word epsilon if I is equal to 0. And it is L concatenated with L to the power of I minus 1 if I is greater or equal to 1. Now this looks sort of like a kind of silly, overly complicated way of doing things, but it also indicates that there are some significant differences between the powers of a number and the power of a language. If you take a number x and you take it to the power of I, that tends to conform to that definition, except when x is 0. If you have 0 to the power of 0, for instance, well, that really, you don't know what that is. And mathematicians tend to be shying away from telling you what this is because they can't really define it very well. In the case of languages, that is entirely irrelevant. So it is perfectly possible to take the empty language and take it to the power of 0. And by definition, this is the language consisting of the empty word. This follows directly from that, because this is for any language. And since the empty set, as we pointed out before, is a perfectly good language, as is A star, we can certainly assume that L is the empty language, and by definition of the power, taking the power of a language, if I is 0, then regardless of what L is, the result of taking that language L to the power of 0 is epsilon, the language consisting of epsilon, and so that is true even if L is the empty language. So if I take the empty language to the power of 0, I will always get the language consisting of the empty word and nothing else. So it is important that you understand that the language that is empty is very different from the language that consists of the empty word. That language contains nothing. This language contains one word. It happens to be the empty word, but it contains one word. So this, the cardinality of the empty language is 0. The cardinality of the language consisting of the empty word is 1. And so if I take that empty language to the power of 0, then I get the language that consists of the empty word, which is a language one element. Epsilon is a word with 0 letters, exactly, but it is a word. Just like 0 is a number. Okay? So, now we can define L star. L star is then a language that is an infinite union, I greater or equal to 0, L to the I. You have to think a little bit about that. This basically says we'll take L to the 0, union L to the 1, union L to the 2, and so on, and so on, and so on. Now, it is, of course, not very difficult to verify that L to the I, say for 2 or 3 or 4, is L concatenated with itself I time. So if I have L to the 4th, well, that happens to be L concatenated with L concatenated with L concatenated with L. Why? Well, you can go into the definition. L to the 4th is L concatenated with L to the 3rd, by definition, which then is L concatenated with L.
Hello?
I think you're muted again.
Thank you for letting me know. So we have L to the 4th, which is L concatenated with L to the 3rd by definition, and then we take the L to the 3rd and use the definition, so that gives us L concatenated with L concatenated with L to the 2nd. Then that gives us L, apply that definition to L to the 2nd again, that gives us L concatenated with L concatenated with L concatenated with L to the 1st, and then L, this is now a little bit kind of stupidly redundant, but the definition forces us to do that. We now have to take the definition for L to the 1st, which is L concatenated with L to the 0th. So we have those 3 copies of L, followed by L, followed by L to the 0. And now, of course, we get L concatenated with L concatenated with L concatenated with L concatenated with the language consisting of just the empty word. And so what that means is we now have to know what happens when we concatenate any language with the language consisting of epsilon only. Well, that, of course, means we go to the definition. So if we have any language concatenated with the language consisting just of the empty word, that means that second word, V2, is simply going to be epsilon. So we have the set of all V concatenated with epsilon, where V is in L. And that, of course, is L, because V concatenated with epsilon is V for all V in L, and so that gives us L. And that means we can do the same thing from the other side, epsilon concatenated with L. That's, we have now in this case, epsilon is V1, is V, the first word, and the second word ranges over all elements in the language, so that obviously is again L. So the language consisting of epsilon, the empty word, is acting as a 1 in multiplication. Now, if we look at the other language, L concatenated with the empty word, empty language, well, what is that going to be? Go to the definition. Basically says you take a language, a word from the first language, which in this case is L, and you take a word from the second language, which in this case is the empty language. Well, how many words in the second language are there?
None.
None. So how many words can I form? None. Which means I have the empty language as the result. And of course, if I do it from the other side, then I'm going to get the same thing. So if I take the empty language and contrast it with the language consisting of the empty word only, then it is glaringly obvious that they behave very differently. If I concatenate any language with that language consisting of the empty word, then I basically preserve the other language. So this is, in some sense, acting like the numeral 1 in multiplication. On the other hand, if I have the language consisting of nothing, the empty language, then that acts as the numeral 0 in the realm of numbers. So if I take any number multiplied by 0, I obviously am going to get 0, and again I can get it from both sides, and I get the same thing. So it should be very obvious that now, going back to this, I basically have 4 copies of L, which is a very complicated way of saying that L to the 4th is 4 copies of L. And so what this definition then says is that I am looking at all possible combinations. I take the empty string, which obviously is always in L star for any language L, because obviously by definition this is a union and I starts at 0, so I have L to the 0, and that is the language consisting just of the empty word. So obviously the empty word is guaranteed to be in L star for any language L, including L being the empty language. And then we have L1. Well, that's basically just L. We have L2. That's basically LL. And then we have 3 L's and 4 L's and so on. So this is clearly an infinite union. And that then defines the star. So what does that mean? Well, we basically now have 3 operations that will be haunting us from now on. We have union, we have concatenation, and we have star. So the union is, of course, what we just discussed. inherited from the fact that these are set operations and each language is a subset of A star. Concatenation comes from the concatenation of words. There is the definition. And the star definition is the most complicated one. Now,
Professor?
Yes?
So L star would also include the empty language? Or no?
The empty language is always a subset of any language. But what you are suggesting is probably not what is correct. When you say it includes the empty language, you mean it would be part of that union. Well, the problem is any set contains as a subset the empty set. So obviously the empty set is a subset of any language.
So all languages contain L star?
No. That I'm struggling. I sense that what your question is, the empty language a part of L star, is very misleading, because we're not saying that this is part of that. Okay, the definition of L star is given this way. There is no empty set. The empty set arises simply because it is contained in any set. Any set contains as a subset the empty set. So this is always true, but you're not going to list that empty set in that union, because there is nothing that L to the power of I is not going to give you the empty set unless your L happens to be the empty set.
Okay, I understand. Thank you.
Okay, so I'm all right. Did I answer the question, or are you?
So I understood that L star is not the empty language, but what is it?
L star can never be the empty language, because by definition it will always contain the empty language.
Okay, that makes sense.
Because that's what it says. This is the union I from 0, 1, 2, 3, and so on. And so L to the power of 0 is the set consisting just of the empty word. And therefore, regardless of what L is, L star must contain epsilon. Okay?
Okay, that makes sense. Thank you.
All right. So that means we now have the definition of the star. We typically are going to be concentrating on those three operations. As I said, we also have intersection and we have complement, and occasionally we will refer to them, but most of the time we will be primarily interested in union, concatenation, and star.
Hello?
Again, somebody muted me. issue here is, let's look at, well, first of all, you've already seen the star operation in action. It didn't look that way because basically I just said A star is the set of all finite words over A star, over A. But actually, if you think about it, it is precisely that definition that comes into play. So if I look at A star and I look at that definition, then I basically get epsilon. This is A to the 0, union A, which is A to the power of 1, AA, A2, A to the third, and so on. So clearly this is all the words that you can possibly have. If you have a word of length 10, then it is in A to the 10th. And so while originally it looked as if we simply defined A star as the set of all finite words over A, that's not really the correct way of looking at it. This is in fact, the A star is in fact that star operator in action. So let's look at a couple of simple examples. Suppose we have two sets. We have letters and we have digits. So this is L, A through Z, and D 0 through 9. And so now let's think of a simple programming language, and we want to define what is an identifier. Well, in most programming languages, identifiers typically have to start with a letter.
Your screen's totally black.
Okay.
We're good now. It's okay now. It went away. We're good. Thank you.
Sorry, I don't know what. So let's define the alphabet A through Z and the letters 0 through 9. And let's see how we can look at an identifier. Well, an identifier, as I said, should start with a letter. And then it can have any number of letters or digits afterwards. So we can very simply describe that in the following way. It has to have a letter. And then it is concatenated with either letters or digits, 0 or more. And so what you have here is a complete description of all identifiers. In that simple language, which we said, an identifier has to start with a letter, and then it can have any number of digits or letters after them. So that means if there is a word in that language, then it has to be cut into two pieces. So there is some V1 concatenated with V2, and the V1 has to be a letter because it is an element of L. And the V2 then can be anything in that star, L union D, which means any letter or any digit 0 or more. Star, of course, is 0 or more. And so this is a complete description of all possible identifiers in that simple programming language. Let's look at another example. Let's take an integer. Well, an integer obviously has to have a digit, and then it can have 0 or more additional digits. So this is a definition of all integers. So what about reals? It gets a little bit more complicated. So we have to have digits, and we have to have a decimal point. And so you might start by saying, well, how about d star, decimal point d star? That, of course, is wrong, because it would say a real is simply a decimal point, because I can pick epsilon for the first d star and epsilon for the second d star, and that means I would simply have the decimal point and nothing else. That obviously does not qualify as a real number. So what we have to do then is we have to have at least one digit followed by d star, followed by the decimal point, and then 0 or more. Or we could have d star, decimal, and then d with d star. So that will permit us to have something like 1 point or 0.5. 1 point would be in here. Okay, there's one digit followed by nothing, followed by the decimal point, and then no digit after the decimal point. Or 0.5, that would be in here. We pick nothing, epsilon, before the decimal point, and then we have one digit, and that would be here, and then 0 or more. So in this case, we go for 0, and so 0.5 would be in here. So that would then be actually a workable definition for a real with a single decimal point. This is not going to work. Everybody, is that clear?
Yes.
So now we have to do something that, because we won't have time to finish that today. But I've already said that we have infinite an infinite number of words, and the number of words over any alphabet is countably infinite. And I already indicated how you do that. You can group things, you can group words into words of length 0. There's only one, there's epsilon. Then you have groups, the group of all words of length 1. It's basically one single letter. So if you have C elements in the alphabet, then you have C words of length 1. And then you have all words of length 2. Again, if C is the cardinality of the alphabet, then you have C squared words of length 2, and so on and so forth. So in this way, you can sort your words into words of increasing length, length 0, length 1, length 2, length 3, and so on. And within each group of a fixed length L, you can then apply lexicographical ordering if you impose a particular ordering on the alphabet. So ordinarily, if you have the alphabet as binary, then you would say 0 is less than 1. And so if you then have a group of length 3, then 0, 0, 0 is less than 0, 0, 1, less than 0, 1, 0, less than 0, 1, 1, less than 1, 0, 0, less than 1, 0, 1, less than 1, 1, 0, less than 1, 1, 1. So there are these 8 word binary strings of length 3, and if you impose that particular ordering on the alphabet, then that induces the ordering, lexicographical ordering, on the strings of a fixed length, and so in that way you can assign to each string a particular number which corresponds to its position in this enumeration. So that means the set of all words over A is countably infinite, and that means we can write down an enumeration of all words. So we have epsilon, then 0, then 1, then 0, 0, 0, 1, 1, 0, 1, 1, and so on. So here we can write down, and of course I do that for A is equal to 0, 1, but you can do that for any alphabet. I can enumerate all the words in A star. So this is an enumeration of A star. And that means every single word that is conceivable will appear in that enumeration. And that, of course, is what is implied when we say that we are talking about a countably infinite set. So this would be 1, this would be 2, this would be 3, 4, 5, 6, 7, and so on and so forth. So, importantly, any string, any word will appear in that enumeration. And that is, of course, the fundamental property of a countably infinite set. I can assign to each element in that set a unique integer number, and I will get everything, so there are no duplicates, and everything has a number. So that's what is meant by enumeration of A star. So the question then is, we have these languages. So L, a subset of A star, is a language. And how can I describe a language? Well, I can obviously describe a language. If I have a language here, I can take a look at each of those words in A star, and I can record whether or not this particular word is in the language. So if epsilon, for instance, is not in L, I would write 0. If 0 is in L, I would write 1. If 1 is in L, I write 1. If 0, 0 is not in L, I write 0. And if 0, 1 is not in L, I write 0. And if 1, 0 is in L, I write 1, and so on and so forth. So what I am constructing therefore here is an infinite binary vector in which so I have B1, B2, BI, and so on. So this would be a representation of that language, such that BI is 0 or 1, and that would be VI.
You're muted.
Thank you. So that binary vector that I'm constructing is then a representation of that language. So I have these words V1, V2, V3, V4, V5, V6, etc. And if a particular word is not in the language, then I write a 0 for that bit. And if it is in the language, I write a 1 for that bit. So BI then is 0 if the word VI is not in the language, and BI is 1 if the word VI is in the language. So it follows, therefore, that I can look at all these vectors, infinite binary vectors, infinite, of course, because the number of words is infinite. Binary because we need only two possible states. Either the word is in the language or the word is not in the language. If the word is in the language, then we need a 1, otherwise we write 0. So we have a binary vector that represents this language uniquely. So if I have two different binary vectors, I will have two different languages. And so now the question that we will have to resolve, and we will do that obviously not today, but on Wednesday, won't all languages contain epsilon? No, they don't have to. If I say I don't want epsilon in the language, then I don't need it. I mean, the empty language obviously doesn't contain anything. In particular, it doesn't contain epsilon. Don't be fixated about this epsilon. This is just another word. It may or may not be there. So in this particular case, epsilon is not in it. And so the question then is, given that we can enumerate all words, can we possibly also enumerate all languages? Are the languages countably infinite? Sure, why not? Well, I'm afraid I don't have time to do that today. We will answer that question on Wednesday. Are there any questions?
Could you go over the PowerPoints one by one? Is that possible?
What do you mean? You
Just
mean show them to you so you can take pictures?
Yes.
Sure. What you suggested was that I repeat the entire lecture, which I obviously can't. Okay, going to 2. Going to 3. Going to 4. Going to 5. And the last one, 6. All right?
Yes, thank you.
Any other questions? All right, then I will talk to you on Wednesday.